introduction. I'd like to thank the organizers for putting together this beautiful workshop and for the invitation to be here and help celebrating Eduardo's birthday. So I too have a connection, if this works. Just says a sound, though. Wow. Nope. Oh, all right. Okay. No? The other one. All right. Great. Thank you. So, my story with Eduardo, I was a student in Campinas working on quantum chaos, nothing to do with correlations or whatsoever. But I took his famous, now famous, Medibody course in 1998. So this is his handwriting, the first ever note. So he starts essentially writing some sort of theory of everything Hamiltonian and say that we cannot solve it. And then, of course, these notes, I kept them for many years, like for 25 years, and they were really helpful when it came my time to teach this course at USP here in São Paulo. And here at USP in São Paulo, they had this, very strong electronic structure group. And so the students, when they talked about condensed matter theory, they would immediately think DFT. So this a course like that, quantum Medibody, hasn't been taught at USP here in São Paulo for like 12 years before I came. And now I'm actually passing the torch to Eric, who's going to teach it next year. But I took a lot of inspiration for Eduardo's course, including the problem sets. Like this is the very first problem set on bosonic coherent states. I'm not sure if it still is in your problem sets, but in mine is the first one. So, and of course this, in this course, remember 1998, was very important to me because it opened a whole universe in terms of physics, which I found it very useful later. And it was the first time that I heard about the Anderson model, or the Kondo model for that matter. And learning about the Anderson model in 1998 was a really good timing because, as Carol showed us, two key experiments on Kondo effect in nanostructures were published that very same year. The experiment by Goldhaber-Gordon et al. On the Kondo effect in quantum dots was published in January 1998. And the experiment by Michael Cromie's group at Berkeley on the Kondo effect in magnetic atoms on surfaces was also published in April. So remember, this was the first semester of 1988. Everything was happening at the same time. And later on, I myself came to work on Kondo-related physics. And you can trace a direct line from what I learned in that course to what I used later in my career. So thank you, Eduardo, for expanding our horizons. All right, so enough of the stroll down the memory lane. Let's talk about these parafermions. And I'd like to thank both Rebecca and Mucio for talking about Majoranas. So here's a quick crash course on parafermions. So let me start with the simplest parafermions of them all, which is the Majoranas, the Z2 parafermions. And as we heard about, and essentially I'm going to introduce the parafermions as I understand it. So I'm not I don't have a deep understanding of clock models and all that, so I'll try to make a parallel with fermionic operators and how you relate them. So of course we know about fermions, right? You have these two-state Hilbert space, and you have these properties of which bring the statistics, like the anti-commutation relation, C dagger square equals C square equals 0, and you can define a number operator and also a parity operator. If you don't believe me, you can go into Eduardo's notes. It's right there as well. And the Majoranas is essentially a different representation. You can write your Majorana operators in terms of these guys. So how do you do that? Essentially, they obey this algebra. They are real operators. So the Majorana, you dagger Majorana, you get itself. And you have the algebra, which is different, a little bit different than what you get for regular fermions. For instance, if you square a Majorana, you get 1, not 0. But they have, these exchange statistics with a minus sign here. And of course, you can build up a Majorana out of regular fermions this way. You add the particle or your full glass, and you add the antiparticle, your empty glass, and you get a half full glass. And if you dagger the half full glass, you get a half full glass, right? So that's the magic of the Majoranas. Now, how about the Majoranas and the Kita-F change, which we also heard about it. And there's a nice trick that if you take this 1D P-wave superconductor and with spinless fermions, and you write these operators in a Majorana basis with a phase very conveniently chosen like this, you get a chain of Majorana modes or Majorana operators that have essentially 2 phases. There's one phase which we call the trivial one, which is, you can say that you have on each site of this tight binding chain, these Majoranas are very well coupled, so you can call that strong coupling. And it is essentially the textbook definition of an insulator, right? Fermions localized, not talking to each other. And so there's a gap, but it's a trivial phase. But of course, there's another phase where you can choose your parameters for this Majorana chain here in such a way that you strong coupling every other Majorana in the chain, and you leave 2 of them hanging on the edge of the chain. And so this is also a gapped phase, but it's topological in the sense that you have, for instance, these edge modes sitting at the edges of the chain. And of course, there's been, this is, was the Kita-F proposal of, 22 years ago. And there were several proposals as to how to realize or to create a system which would have, at low energy, the same properties of the Kita-F chain. And so far, the results are mixed, to say the least. And in practice, there was a big blow into the field by the retraction of this high-profile Nature paper in 2018, and which turns out that these results suffer some sort of bias or confirmation bias, if you wish, and the systems the signatures are not as easy to interpret or to say if you found a Majorana or not as people originally thought. To the point that there's now this sociological discussion of where the field is heading, and to give an idea of how things are at this point, we had last year this paper by Microsoft, essentially, 120 authors. So it's like high-energy physics, right? And the jury is still out if they say, okay, now they develop this very complicated protocol to determine whether the experiment signature is a Majorana or not. And we still, lots of controversy. This paper, I checked yesterday, has not been published yet. And of course, you have social media in between, like, for instance, Sergei Frolov, and all the discussions that I think is necessary as to avoid things like confirmation bias in experiments, especially in journals like Nature. So there's a whole other topological or sociological discussion that I think is permeating the field. So I work on this for some time, and that's why I turn into more basic questions. And the parafermions are, I'm going to argue, are in a similar state today as the Majoranas were like 20 years ago. So I try to think more in terms of these things where we can at least have some very fundamental questions that have not been understood. And one key trick I'm going to use throughout the seminar is do some sort of reverse engineering of something like a Kita-F chain. So let me walk you through it. So imagine that you are maybe Alexei Kitaev, and you're sitting there and say, okay, let me write a tight binding model of Majoranas, and let me start from one of the topological phases that I know exists in this model. What is the corresponding fermionic model, right? So you can do the reverse of what I just showed you, and you write the Majoranas in terms of spinless fermions, and you get to a 1D P-wave superconductor, right? So this is, of course, these two is just a mapping. So you can try to find the topological phases here in this model that would correspond to this one. So that's something that we're going to do in the context of these parafermions. So let me now try to define what these parafermions are. So they are like the Zn cousins of the Majoranas. So let me start with the simpler one, which is the Z4 parafermions. And the trick here I'm going to use is this idea of Cabanera and Ortiz that define a operator that has a Hilbert space, that you can create a Hilbert space with it and use that to create the actual parafermions. So imagine you have a D operator that you, or a D dagger that you apply to the vacuum, and you get state 1. Apply D dagger to 1, get 2. D dagger to 2, get 3. And when you apply D dagger to 3, you get 0, right? And then your D operators obey this algebra here, and you still can define some number operator and a parity, right? Now this parity, so quote unquote, will have, of course, you have Z4, not just +1 or -1, but in principle you have everything that you need. The algebra here is close to, so that all this works in this Hilbert space. Now, you can define your parafermion operators by using these D operators, these Fock parafermions, the same way that you define Majoranas in terms of regular fermions. Now, what you get when you do that is precisely the properties that we want from parafermions, or Z4 parafermions, that if you take them to the 4th power, you get 1. And if you dagger them, you get the actual operator to the 3rd power in both cases. And everything works nicely in this algebra. And now here you have anionic statistics right off the bat, because if you exchange two of them, you get to the e to the I pi over 2 and not just -1. Yes? Okay. In different sites, you mean? Yes. That you might get strings, and I'm gonna get to that. There's a rule that, of course, if you put indices here, I don't remember by heart what you get out of here, but you might get no local computation radiation, and that can be a problem. Not in this case, but in the Z3. So I'll go back to that. So one thing that I should point out here is that the algebra of regular Majoranas is somehow hidden in here, because if you take this guy squared and you dagger it, you get itself. You get essentially itself, or if you take this guy squared and you square it, you get 1. So there is a hidden Majorana algebra here, which actually makes things easier when you try to write this in terms of regular fermions. Okay, so now the question is, and some of the basic questions that we're asking when we started this project, it was the PG project of my student Rafael, is can you get a Kitaev-like Z4 parafermion chain out of regular fermions, right? Not these D operators, but actually regular fermions. And it turns out that you can do that reverse engineering trick that I told you about. We just write a Kitaev-like chain of these parafermion operators here. Oops. Sorry. And we choose it to be in the topological phase with these two parafermionic modes sitting decoupled at the edges of the chain, and we do a reverse engineering and see what we get in terms of actual fermionic modes. And for that, we need to write those D operators into those D operators in terms of actual fermionic modes that would obey that algebra that I showed you about. And there's a representation which involves single and triple combinations of fermionic operators with spin now that will indeed obey this trick that I want, like a four-site local Hilbert space. So my four states are up, I up, down, minus I down, and 0, of course, the vacuum. And so what I can do is I now can write these guys in terms of the actual fermionic modes and do the reverse engineering. So it's a lot of calculations, and the hope is that you get to a actual fermionic Hamiltonian that can be mapped into this Kitaev chain, at least in some limit. And when you do that, it turns out that luckily we don't get any string terms, no local string terms in this case. This actually had been done before by this group, by Thomas Schmidt at Luxembourg. And let me walk through what you get for the fermionic model. So the first thing that you get is a P-wave superconductor, but now with spins. So you have essentially two copies of your Kitaev chain. Now, of course, these are all one-body terms, but you also get interactions. So you have electron two-body electron interaction-like term is not in the standard way. Is that it has this assisted hopping, if you want, times a number operator. You also get some sort of two-body P-wave pairing as well. So like a P-wave mediated by N. And you have some three-body terms as well appearing, some sort of kind of a spin orbit, like so you have spin flip on separate sides, and you have a square here that complicates things. But in principle, all this is the exact mapping that you would get from the Kitaev chain. And then, and of course, you have also a P-wave pairing-like term, but now is a three-body term. So this is all very complicated interaction terms, if you want, but in principle, is a Hamiltonian that you can put in a computer and solve, say, with DMRG and see what you get. And from that, we can figure out at least some limiting cases where you know which phases you should be getting. The first thing is if you set the coupling, and here I'm calling all the strength of all these interacting terms here just as W, and the P-wave pairing term as delta, and just the hopping T. So if you kill these two guys, you just have a tight binding module, you have a trivial metal. If you kill this guy, and you keep your two Kitaev chains for P-wave superconducting, you have 4 Majoranas, right? So 2 copies of your Kitaev model. So this is essentially what is a gapped system, is non-trivial, but it's just 2 copies of your regular Majorana case. Now, if you make all T equals delta equals W, now you map into the Z4 Kitaev chain, and you should have a gap system with parafermionic 0 modes at the ends of the chain. So we can go with DMRG and numerically calculate this sort of phase diagram and look at these corners. So W equals delta equals 0 is right here, so that's a trivial case. W equals 0, delta equals T, you're here, so it's what you call 2 times Z2 a phase, and you have the Z4 phase right up on this corner. So our goal here is to see whether we can define these phase diagrams by putting some sort of probe attached to the system. And the probe would be, like in Mucio's case, a quantum dot connected here to the edge of the chain. And then we'd like to see, yes? Yes, the Z4. Yes. So 2 times Z2 is 2 copies of Kitaev chains, 1 for each spin. Yeah, essentially. Okay, so here, essentially, these are gapped. So you close the gap and you go from one to the other. So that's, yes, yeah. So that's what we want, and to see if you attach the quantum dot there and just look at the local properties of the quantum dot, whether we can reproduce that phase diagram or not. And so we do exactly that. Now we have also interactions in the dot, and we want to look into, say, the zero energy spectral density or the local density of states at the dot, and see what are the signatures that appear as we go from one phase to the other. And essentially, this is what we get. So this is what I'm plotting here is essentially the height of the local density of states as a function of these parameters at minus U2/2, right at this point. So here, right at this point, you can easily differentiate the phases. Like this is the 2 times Z2, which is the red triangles, and this is the Z4. So it's about, maybe a third of the height here. And I'm going to talk about the shape a little bit later, but this is what you would get for the trivial case. You get 0. So in principle, if you now tune the parameters, you can get a pretty decent mapping of the phase diagram just looking at the local density of states in the dot. And the other thing that comes for free is that if you look at the local density states of the first side of the chain, there's also a difference between this case or this case. So in the Z4 phase, you get a peak here, which is essentially a signal that there is a parafermionic mode right there. And if you're here, you get essentially nothing. It's kind of a cancellation of the signatures that you get from the Majoranas. But you can distinguish that not only on this side, but also at the dot side. The other thing that you can do, and of course you say, okay, well, but in an experiment it's really hard to define the height. So is there any other signature that this is telling you that differentiates red and blue? Another thing is that kind of the curvature. I mean, if you take, say, the difference between this curve minus this point around this region, you can see that the curvature, or the second derivative, if you want, is very different whether you are in the 2 times Z2 or in the Z4 case. And so this could be another signature. And the third signature that you get would be in the dot occupation that you could measure, say, as a function of gate voltage. And depending on whether you are, in which phase you are, these curves are slightly different. If you just look here, the raw occupation with your naked eye, you don't see it. But if you, say, subtract these, the trivial case, which you could use as your standard from the other two, you would see that you can differentiate via the charge, which can be a very, very precise measurement between whether you are on a topological phase or not. Okay, how much time do I have? 8 minutes. Okay, plenty of time. Yes, please. Sure.
Thanks. Just a question from a simple-minded thought. Instead of studying this complicated model, suppose you studied a 1D spinless P-wave superconductor, but with charge 4e rather than charge 2e, which has a Z4 symmetry. Would you realize such parafermions? Is that known, or that's at least somewhat physical?
Yeah, it could be. We have to try, and that's a good question, because as will be clear in the Z3 case, the models that we get using this procedure, they can be very complicated. So there are perhaps simple models there. And one thing that we could try is to calculate, both models, try to interpolate between them, and see if they're in the same topological phase. So that could be one.
I agree with you. The problem is that you'll be a four-body term to begin with, right?
But yeah.
Oh, okay, yeah, sure.
You can
sure,
do it.
yeah.
Okay. So yeah, I'm going to use a similar trick here in the Z3. So for the Z3, which is something that really interested us, and so what would be the deal here? Now we do the same trick, right? But now we need a Hilbert space with only 3 states, 0, 1, and 2, with this algebra here. And now your parity has, 1 e to the 2 pi I over 3, e to the 4 pi over 3. And there are no hidden Majoranas here. So you're all out on your own. But in principle, you can construct the operators out of these Fock parafermionic operators the same way that we did with the Z4. You get the properties that, the parafermion to the 3rd power equals 1. You dagger it, you get square. And also you have anyonic statistics right off the bat. Now, how do you get something like this out of pure fermions? So first, why Z3? Well, one thing that Microsoft doesn't tell its shareholders is that you cannot do universal topological computation with Majoranas alone, right? So because, and I think we heard from Rebecca, they are Eisenanions. And so there's some gates that you cannot do with Eisenanions. So ideally, you either have to have some gates which are not topological protected, or you might want to do the holy grail of trying to find a topological quantum computer out of Fibonacci anions, which are much harder. But there's a path. While neither Z4 or Z3 parafermions are Fibonacci anions, they're all Eisenanions, there's a path that you could try to have this condensate of Z3 parafermions and have quasi-particles which have Fibonacci anions statistics. So, all right, there's a path there. It's really hard, but in principle, this is one of the motivations of studying Z3 parafermions. Of course, the question that we ask is, can we get the Z3 parafermions out of regular fermions or in electronic systems outside of fractional quantum Hall states, which in principle they should be there, but just build up something that you can put, say, in a computer and calculate. So that is the whole motivation for us. And the simple question took us, I don't know, maybe a year and a half to just get our foot in the door. And the reason is that, first off, there's no natural basis where you can define these D-dagger operators for the Z3. So you have to pay a price, and at the end, what we did is, the price we paid is to get rid of the double occupancy state. So like in a TJ model basis, you take a local U to infinity, and you are only left with 0 up and down. And then you can define your D-dagger as C dagger up plus C dagger down, C up, and you have the correct statistics, as long as you exclude this guy from the picture. And in principle, you can write your Z3 parafermions in terms of fermions this way. It's just an approximation, but as long as your local Hubbard U is large enough, this should work. Okay, and now we do the reverse engineering, and just naively. And then things really get a mess, because we get essentially 3 terms. We have, of course, we're mapping already in the topological regime. We have, again, the P-wave superconducting parity when embodied, so that's fine with spin. And now you get 2 body interactions with spin flips all over. I didn't write all the terms here, but they all look something like that, so 2 body interactions. And you have this term, which is no local, has strings, and violates parity, right? So, which is not something that you want in an electronic system. So, because at least parity you should conserve. So there are 2 props. So this thing maps exactly here, but then there are these problems, not only these non-local streaks, and is also this parity violating term. We can still put it in the computer and see what you get, but it's not like what we were dreaming of when we started this project. So my student, Rafael, he thought longer and hard about how do you get a more minimal model that at least doesn't break parity. And he came up with an idea which actually complicated things a bit, but at least all the terms are local and they preserve parity. Now you have 3 body interactions, but they're local. And of course, it preserves parity. And one way to think of the previous model is to think that this is some kind of a mean field version of this one, where you take 3 out of these operators and just put in a mean field coupling and do that. And now the thing that was really hard was to show that these 2 models are topologically equivalent, and that this one, while it doesn't maps exactly into the Kita-F chain, does show edge states, and you can go from this one to the other one without closing the gap. And that's essentially what we did. So we studied both models with the MRG, and we saw the topological phase transitions as a function of parameters on each of them. So for instance, we looked at the gap, the energy gap, and see the gap vanishing, at least within our numerical accuracy. We also looked at the entanglement entropy, and you see this peak of the entanglement entropy right at the transition. So this is the model that preserves parity. And while the other one, you're already at the topological phase for any W3 different than 0. While this one, you see a topological transition for W6. So that's one piece of good news. And you see the collapsing of the gap here right at the transition, and the degeneracy of the ground state changes. So there's a second piece of good news. And the third piece of good news is that here, as I told you, there's a topological transition for non-zero W6, and while this is always topological. And the other piece of good news is that if you interpolate from one Hamiltonian to the other, say something like that, you define H prime of X, 1 minus X H1 plus X H2, and you vary X. So here you are at H1, here are H2, and you look at the gap, and there's no gap closing going from one to the other. Tells us that they are in the same topological phase. We can also look at, here it gets a little bit tricky to define a local density of states that would capture the actual parafermion sitting at the edge of the chain, but that's also something that we did, that the green dot would be the exact case of a parafermion strongly localized at the edge of the chain, and these are numerical calculations showing that even though you have a decay into the bulk of the chain, they are pretty much localized depending on which parameters you choose. If you're closer into the boundary or to the topological phase. So that's the main message. We studied these models asking these very basic questions, and I said that there are still very many surprises even at this stage. And I'd like to, of course, thank Rafael Levy, who defended his thesis a couple months ago. He's now going for a postdoc with Andrew Mitchell in Dublin, and I'd like to thank you for your attention.
Thank you, Luis. Questions?
Luis, if you could go back to the Hamiltonian you wrote for the Z4 case in terms of the fermions. I have a very naive question, which is probably wrong, but let me ask you anyway.
Let's see.
Yes, this one. So the terms that are multiplying the two body, can't I try to replace them by like anti-ferromagnetic order, ferromagnetic order? It seems that some of them are exactly that, right?
It could be.
And wouldn't that give something maybe it's the same way that you have the delta, right? I understand that these are not, then you get something that is not interacting, but maybe they're in the same topological class.
You mean do some sort of mean field here?
No, in the other side, right? Because NJ sigma bar,
here.
So if this was a ferromagnet or the other, then the other ones cancel and only that survives. In other words, because N sigma J, when you do Hartree-Fock, right? These are all parameters that you can find. So couldn't you replace the N sigma J's in terms of some collective mode? Then again, maybe that is completely crazy and doesn't matter.
I guess, so could be that you could perhaps look into what is the magnetic phase that this term is favoring, and that would be something that we didn't study the actual magnetic phase here. It could be a way, and then you might come up with a simpler model that is in the same topological class. That could be a very interesting idea. Freeze out. Yeah.
Sorry, I highly doubt you'll find parafermions in Hartree-Fock. I mean, you get a quadratic fermion Hamiltonian, that's free, right?
It's the same way that with the delta, just the Kitaev, you get the Majoranas without having any interaction. Right. Okay, never mind. We'll talk later. Sorry.
Okay.
Thanks. So it's very interesting. So I was wondering if there's any connection with your Z3 parafermion model and like 3-channel Kondo impurities, which are also supposed to have these Z3 parafermions.
So there is this recent paper by Andrew, actually, with Hubbard-Gordon, where they have these double charge quantum dots, and they see a Z3 parafermion emerging out of these 3-channel Kondo. It's very similar. I think it's very similar, to your work, and that one by Komigiani that you cited, where now Andrew tells me that is, we're still discussing because we have this collaboration. Rafael is actually going to work there, and one of the reasons that he was hired is because his experience with parafermions. So the question is how you braid them. I mean, I think I'm pretty sure, the residual entropy shows that there's a Z3 there, and now the question is how do you operate with that? But it's a very interesting way to produce at least these parafermions out of fermionic models as well. So yeah, more complicated, involves 3-channel Kondo, but yeah.
Other questions?
Everybody's hungry.
Okay, if not, let's thank Luis again.
Thank you.